Alright, class, so apparently the other thing cut off and there was no video ever recorded, so I'm just gonna redo that then. So it'll be like 30 minutes or so, but yeah, this is what got missed on the stream. So, going to evaluating and understanding inverse trigonometric functions. So for a regular trigonometric function, what you're doing is you're given an angle and then you're given a function, and you want to find a value related to that function. For instance, if we had something like sine of pi over 6, we know that this is going to be 1/2 because we look at pi over 6, and the coordinates are square root of 3 over 2, comma, a half. So using that, we can easily see that we get 1/2. So if we look down here, inverse trig functions, given the value of a trig function, find the angle that makes that happen. So we're literally going in the reverse. So here we're given, basically this means sine of theta equals 1/2. What is theta? Also, make sure that you know how to read this. This is sine inverse of 1/2 equals or is. Rather than, don't say sin -1 or sine -1 parentheses 1/2 parentheses. Don't call it that. Say sine inverse of 1/2 equals. That's also a lot faster. Okay, so if we look at a unit circle, we can tell that at pi over 6 and 5 pi over 6, we actually have the same sine value. So here, so 5 pi over 6 and pi over 6 both make that happen. If you also look at a sine graph, though, you'll see that 1/2 happens along, let's just say that that line is 1/2. It'll happen at 1, 2, 3, 4, infinite numbers of points because this same behavior is going to happen over and over, right? So basically, that means we have to restrict the function so that sine inverse of x gives us one input and one output. So remember the whole vertical line testing that you've learned in algebra? So if you have something like this, that's not a function because you can draw a vertical line through it and it passes multiple points. Well, the reason for that is because you want it so that if you have one input, you have one output. Exactly 1 to 1. So let's restrict our functions that way. So if we look at this is the sine graph, the familiar sine graph. So basically, we know that sine is restricted, right? So we know that sine of theta is restricted between -1 and 1. So between that max and that min. And we'd have a bunch of maxes and a bunch of mins everywhere. That's just how sine works. So we want it so that the angles, so the x values, are only going to be from a certain region. We don't want all of them because, again, we just want one output if we put an input. So like if I said a half, we want only one value to get here for 1/2. So that'll be either here or here or here, but it doesn't really matter technically where it is. So what mathematicians have done over the ages is choose a specific part for it to happen. That part is here. So from -pi over 2 to pi over 2. So the range restriction for sine inverse of x is -pi over 2 is less than or equal to y is less than or equal to pi over 2. Alright, so how about cosecant then? So that's what that looks like. So let's get rid of the sine graph and think about, well, what can we do with this thing? So we know that they have these things going on, and basically cosecant is going to be above or equal to 1 and -1. So we want to get all the angles that make all the infinite values like that. And just a quick thing, we are going to choose the same ones as sine inverse. Reason for that is simple. It's just because it's a lot easier to compare them because they are related, right? It's a lot easier to compare them when we have the same exact thing. So the same exact restriction. So for sine inverse and cosecant inverse. By the way, make sure that you don't think that this is the cosecant inverse graph. We're using cosecant to get the cosecant inverse restrictions. Alright, point is, that's the restriction. So know this. Alright, so now let's look at cosine. Cosine is also bounded like sine between -1 and 1. So let's look from all of these. And so mathematicians chose this as the restriction for sine because it was the most centered one, the one that's closest to 0. Here we don't exactly have one that's necessarily closest. We have -pi to 0 and then 0 to pi. Well, the question is which one do we choose? Well, that one's easy. You want to use the positive one just because why not? So the range restriction for cosine inverse of x is going to be from 0 less than or equal to y is less than or equal to pi. Just easiest one to work with. And then secant inverse of x. Let's look at that thing. So the graph for secant is that. Remember, this is not secant inverse, this is secant. It is also similar to sine inverse where it has those points at -1 and 1 and then just goes to the infinities. So similarly, we are going to choose the points that are, or the angles that are within this specific range. So exactly the same. Technically, though, you have to say except pi over 2. And up here, you technically have to say except 0, just for the cosecant inverse graphs, just because it doesn't happen. It's undefined. Alright, so now I'm going to go to the next one and talk about that. Alright, so tangent, this is actually a lot easier than one would think. -pi over 2 to pi over 2. Basically, within the asymptotes is just one period, right? If we choose between there, we're going to get the entire thing. So the range restriction is going to be so be careful with this one. This is pi over 2, -pi over 2 to pi over 2. So the thing about that is it's not equal to. So make sure you don't write that. That will be considered wrong if you do it. The reason is because over here, -pi over 2, positive pi over 2. Is tangent equal to it there? No. And basically there's no value that's going to make tangent inverse equal pi over 2 or -pi over 2. So there's that. Well, let's look at cotangent then. This one, yeah, that's going to be interesting. But basically, it's not going to have the same restriction. It's going to be different, right? Again, with the whole asymptotes, just choose between there and then you'll get it. Here we want to use 0 to pi. So the range restriction for cotangent inverse is 0 to pi. So make sure that you are aware of those so that when you're doing these, you'll be able to get the correct values. Because, yes, you will be marked wrong if you are getting the wrong values. Because, well, obviously it's wrong. So, yes, be aware. So, let's practice that then. I'm going to recall each of those as we go on here. So, for the cosines, that's going to be between 0 and pi. By the way, this is what's called interval notation. This is equivalent to saying that. Just for space reasons, I'm going to write that in this area as we do this. So 0 to pi inclusive. By the way, for things like cotangent, it'll be that. This just means not equal to. Alright, so cosine inverse of a half. So cosine is 1/2 when your angle is pi over 3. So you can write that cosine is equal cosine inverse of negative 1/2. So cosine is equal to 1/2 when the angle is 2 pi over 3. And remember, we're choosing between those. So technically, negative pi over 3 also works for 1/2, but it's out of that range. For this one, you can also say 4 pi over 3, but it's out of that range. Therefore, we don't choose it. All right, tangent inverse. So tangent inverse is going to operate from negative pi over 2 to pi over 2. So where is tangent equal to 1? That's going to be at the pi over 4s in the first and third quadrant. But we're looking at these, which is only from the 4th to 1st. So pi over 4 is going to be the correct answer for that. All right, secant inverse. That's going to be from 0 to pi. Secant inverse of 2 over square root of 3. So cosine is negative square root of 3 over 2 at 5 pi over 6. So that'd be correct over here. Sine inverse of 1/2. Oh, by the way, notice I referenced cosine for secant because cosine and secant are reciprocals. All right, sine inverse of 1/2. Sine is 1/2 when the angle is pi over 6. If we're looking between negative pi over 2 and the pi over 2. All right, cosecant inverse of negative square root of 2. So cosecant is reciprocal of sine. Sine is negative 1 over square root of 2 at negative pi over 4. And since it's reciprocal, basically the same thing. All right, cotangent inverse of negative 1. Cotangent and tangent, they're related. They're both at negative 1 at negative pi over 4. Well, technically, yes. However, cotangent, remember. So that's like a little trap there. Is only going to be defined from 0 to pi. So we can't use negative pi over 4. But there is another angle where that happens. That's actually at 3 pi over 4. So let's use that. So, secant inverse of the square root of 2. Cosine is 1 over square root of 2. So, cosine is the reciprocal of the inside here when the angle is pi over 4. So, we will choose that. Tangent inverse of 0 is 0. Cosecant inverse of negative 2, that'll be negative pi over 6. Alright, so hopefully this makes more sense right now. Yeah, just make sure that you understand all of these. If you know all of these range restrictions, that helps significantly. So I'm going to give you like 5 seconds to take a picture of this if you need it. All right, next one. Same thing, 5 seconds to take a picture if you need it. Actually, you can just pause the video, so. Okay. Pause the video if you need to. Okay, moving on. Okay, transformations. Oh, this thing. So, transformations. Essentially, a transformation, which we will call y, of a function, which we will call f of x, is in what's called graphing form if y equals a times f of the quantity b times the quantity x minus h, all plus k. So what in the world does that mean? Well, there are a few things that happen here. We have some things called parameters. That's what the a, b, h, and k are. And they do different things to the function. Depending on where they are, they do what's called scaling or translation. Not necessarily where they are, but more like what operation is happening. A is multiplied to f. So a is multiplying to the y values. So vertical, scaling. Scaling just means multiplying. So stretching or shrinking. B is multiplied inside of f. So it's affecting the inputs. In other words, the x values. X values, x is horizontal, left and right, correct? So therefore, the b value is going to do a horizontal scaling, so stretch or shrink, by a factor of b. And then h and k, they just move the thing left, right, up, or down. H is inside, again affecting the inputs, so horizontal translation. K is a vertical translation. So if you want to know what all of these things do, you can also look over here. This is what it mathematically means. So, intuitive, mathematical. So if you were to get all the points for a graph, that's what you would get. Alright, so I'm going to walk through an example here real fast. If you needed to pause that to copy that down, just go back to it later on and pause it. And now we're going to work on these. Alright, so I'll walk through this one and then give you one to do. Alright, so let's look at this. Parent function is y equals secant of theta. That should be fairly clear by now. If not, it's right there. Essentially, the parent function is usually pretty clear. It's right there. If you had something like 1/2 x plus 2 all squared minus 5, the main thing that's happening is squared, right? So the parent function is just x squared. Parent function is easy and also very necessary. Whoops, I erased the parent function. Okay, so transformations. The first thing that happens is the 1/2. So that is a vertical shrink by a half. Alright, what's next? We get that 2. That's going to be a horizontal. That's actually a shrink. Alright, and then the next thing that we have here is that pi over 2. That's going to be a horizontal shift. Pi over 2 units left. It's left because this value itself is negative. Because remember, you have theta minus h. If h is negative, so if h is negative pi over 2, moves to the left. If h is positive, so we have theta minus pi over 2, we go to the right. Alright, and then last thing, this 2. That's going to be a vertical shift 2 units down, because you're subtracting 2 from all the y values, basically. So everything's going to move down. So I'm going to do all the points here, like that whole thing. And then for the next one, I'm going to kind of just like work on it logically rather than points-wise. but like kind of as well. So we're going to want to have 3 asymptotes here. And then there are going to be 2 important points. Let's look at the secant graph and see what I mean by that. So this is the secant graph. We see that we have 1, 2, 3 asymptotes within a period. Remember, this is 1 period, 2 pi. And then there are 2 important points there. There's the one that leads to that U-shape and the one that leads to the other U-shape. So if we get those 3 asymptotes and those U-shapes, or at least the points for them, then we'll be able to get the entire graph. So let's go down. The asymptotes are at, let me just center this better, negative pi over 2, pi over 2, and 3 pi over 2. And then the points are going to be at 0, 1, and pi, -1. Okay, so this is the parent graph. So let's see what happens when we transform it. So with this is what's happening when we have the vertical stretch. So what we're doing is we're multiplying the y's by 1/2. So that does not affect these 3 values because those are x's. It even explicitly says x. So 1/2 to those. So we get 1/2 and -1/2. And the x value still stays the same. So let's just write those in. All right, and then this. We're going to, as I said, divide x's by 2. So that's going to change. But what doesn't change is the 1/2 and the -1/2. They just stay like that. All right, so 0 and pi, they're going to change. Divide them by 2. 0 over 2 is 2. Pi over 2 is pi over 2. And then remember, dividing by 2 is the same as multiplying by 1/2. So if you were to do that on all of them, then you would easily get negative pi over 4, and 3 pi over 4. All right, got that. Now let's move on to the next thing. We're going to move this horizontally. So moving it horizontally to the left, that means we're going to add the h value. So add negative pi over 2. Remember, that's the same thing as subtracting. Do that to the x's. Okay, so that means, again, the y's are going to stay the same. X's, they're going to change. So if we're subtracting pi over 2 from all of those, well, these 2 are easy to do. 0 minus pi over 2 is obviously negative pi over 2. Pi over 2 minus itself is obviously also going to be a value, 0. All right, and then here, you might be like, oh my gosh, what to do? But remember, fraction minus fraction, common denominator. This is an easy common denominator to get. So we get negative pi minus 2 pi. Negative 3 pi divided by the denominator, 4. And then pi minus 2 pi. We get negative pi over 4. And then here, you get 3 pi minus 2 pi, which is obviously negative pi over 4. So that calculation should be fairly quick by now. Again, we spent 6 weeks in the beginning of the year going over fraction arithmetic. All right, then the last thing over here, we're going to be adding negative 2. So adding the k value. In other words, subtracting 2 to the y values. Okay, so these asymptotes, they're just going to stay the same because they are x's. And those values will also stay the same. And then we're subtracting 2 from these. Yay, more fraction math. So 1/2 minus 2, that should be easy to do. That's get a common denominator. So that's 1/2 minus 4 over 3. I probably don't, 4 over 2, sorry. I probably don't really need to do that, but there it is. Okay. And then negative 1/2 minus 2. You should be able to pretty quickly get that as negative 5 over 2. Alright, so I'm just going to copy this over to the other part so that we can use it. And then get rid of some parts of it just so that we have space. So going to get rid of this. You don't need that by now, and if you do, rewind the video and just copy it down again. Whoops, brought the function down. Oh well, we know what this is. Alright, so I'm just going to make my axis. I know we're going to have more on the left side than the right side, so I'll just make it kind of like this. Okay. So make sure that as you're drawing your axis, you make it look neat and stuff, so use a ruler if you need to. Let's see, so we're going to have a lot more on the bottom than on the top. So I guess I'll just make it like there-ish. Because the thing still does curve upward. So we'll need parts on the top. So 1, 2, 3. Let's just do this by 3s. 1, 2. Do it by 4s. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Alright, so that'll be negative 3 pi over 4. That'll be negative pi over 4. And that'll be pi over 4. So let's draw on the asymptotes first. That just makes it a lot easier. So we get one at pi over 4, negative pi over 4. Just gonna make that a little bit less to the side. And then at negative 3 pi over 4. And then, oh, we gotta get the y-axis as well. So we get a bunch of pi over 2s. So let's just do that as, let's see, 1, 2, 3, 4, 5, 6, 7. So that'll be negative 1/2, 2 halves, 3 halves, 4 halves, 5 halves, 6 halves, 7 halves. Negative 7 over 2. That'd be 1/2, 1, etc. Okay. So at negative 1, 2, 3, 4, 5 over 2. 0, comma, negative 5 over 2. We got that. Alright, and then at negative pi over 2, comma, negative 1, 2, 3 pi over 2. We get that. So if we were to draw the graph then, we get something along the lines of this. So they are very close together, but that should make a lot of sense because we did reduce everything by a half. Okay, so last one over here I'm going to do fairly quick. So, quick thing. Notice that for these points, essentially what happened was we did stuff here to the x's, and we did stuff here to the y's. If you can do that all in your head, that also makes things a lot faster. So I'm going to kind of demonstrate that here. But what you should always do is write down the transformations no matter what. Parent function, we get sine inverse of x. Alright, the 3 gives us a vertical stretch by 3. The 1/2 gives us a horizontal stretch by 1/2. And then the -1 gives us a horizontal shift 1 unit right. And then the pi over 2 gives us the vertical shift pi over 2 units up. Okay, so if we think about the important points in asymptotes and whatnot for this, well, let's see. There are no asymptotes anyway. But the important points are negative pi over 2, -1, 0, 0, and pi over 2, 1. So if we transform those, what's happening is all of the x values, we're going to divide by a half and then add 1. Divide this by a half means multiply by 2. So negative pi over 2 becomes negative pi. If we move it 1 unit to the right, oh shoot, that is reversed. Sorry. -1, negative pi over 2. I was thinking sine, but they're reversed, doesn't matter. Okay, so 2 times that is going to be -2, plus 1 is -1. 2 times 0 is 0, plus 1 is 1. 2 times 1 is 2, plus 1 is 3. Alright, so now let's look at the vertical stretch and shift stuff. So we multiply all the y's by 3, and then we add pi over 2. So if we multiply 3 of these, we get -3 pi over 2. If we add pi to it, we get negative pi. 0 times 3 is 0, plus pi over 2 is pi over 2. Surprise. And then pi over 2 times 3 is 3 pi over 2. If we add pi over 2 to that, we get 4 pi over 2, which is just 2 pi. Alright, so now let's draw the graph. It's going to be a little bit more right-sidey. Alright, so just going to draw the axis then. So make sure you are using logic in terms of where you draw it. Don't just draw everything centered. That might not always be the most useful thing. Okay, let's see. So going to be a little more top heavy on the y-axis as well. So I'm just going to make that a little bit lower so we can see things a little bit better. So let's do this by... Let's do that by 3s for each of the increments. 1, 2, 3. 1, 2, 3. I can make that down 1. 1. So that'll be negative pi. 1, 2, 3, 4. So that'll be 2 pi. That'll be pi. And then going left and right, let's see, we'll have... Let's do that by 3s also. Now let's do it by 4s. 1, 2, 3, 4. So that'll be -1. 1, 2, 3, 4. Wait. 1, 2, 3, 4. That'll be 1. 1, 2, 3, 4. That's going to be 2. And then 1, 2, 3, 4. That'll be 3. X and Y. Alright, so plotting the points, we get -1, comma, negative pi. 1, comma, pi over 2. And 3, comma, 2. So, we know that sine inverse has this general shape. And that's what we get. Alright, so hopefully this is helpful. Yeah, obviously no question and answer time because it's not a stream anymore, but rather making it for the stream. Yeah, so leave any questions in the comments. Ask me questions on anything that you have contact with me on, like email and stuff. And good luck on the test. Thank you for watching. ありがとうございました。頑張って、じゃあよ。